Hi, welcome back to my YouTube channel. As you already know, my name is Abdulwahab Anemoku and I'm a college math instructor. In today's video, we're going to look at how to find the domain of the following functions. So these are functions of two variables and we're trying to find what the domain of these functions are. Okay, so let's just get started on the first one. Now, whenever you see a function, the first that you should look out for is whether it contains polynomials or trigonometric functions and so on and so forth, exponential, logarithmic functions and so on and so forth. But for the purpose of this particular question, we're looking at only polynomials, right? And we're trying to understand how they play a role in sketching the domain of a particular function. So now, let's focus on the first problem. The first truth that you have to know is that what all polynomial functions are continuous everywhere. And what this means is that what this means is that what we can evaluate polynomials anywhere at any point right? So an example of that is these two functions. This is a polynomial, and this is also a polynomial. So what is inside the square root is a polynomial. So which means that um, those functions are continuous everywhere. That means we can evaluate them at any point in x and y coordinate system. Okay, so now let's see how do we solve this problem. And the next thing that you have to notice this. So we said polynomials are continuous everywhere. Now the second thing that you have to note is when I have division. So two functions. Okay, so let's say f of x is g of x over h of x, right? Now, when you have this relationship, what usually happens is this function would not be cannot be evaluated whenever the denominator is 0, right? Whenever h of x is equal to 0, f of x is undefined. That is the second thing that you have to note. So which means that what all the values of x that will satisfy h of x will not be in the domain. I hope this makes sense, right? So think about it, because we cannot divide by 0, right? So for a function not to exist, especially when you have them to be when the numerator exists everywhere, what happens is that what the denominator must check for the values of x that will make the denominator 0. And this is the same principle you're going to use in solving this problem. So that's the second thing to note. Now, the last thing to note in this regard would be square root, the square root function. So square root function only exists for reals. For reals, what I mean by reals, I mean that what we're talking about square root in terms of real function, not complex, right? Now, square root function only exists for reals when what? When the inside is greater than or equal to 0. Okay, so if I have square root of any number, so let's say I have square root of let's say square root of let's just say okay, so let me rephrase this. So let's say I have a number, right? So square root of 1. So these are different numbers, right, that we can find possible square root for. Now notice that what we cannot find square root for negative number. This for real, if you check your calculator, this does not work. But yes, this works, and this works. So only when the inside of the square root is 0 or positive do we have a real square root. Okay. So these are the things that you need to take note of while we solve this problem. So let's just get started now on them. So on the first one, the first thing that we note is we have the numerator. So the numerator, so we check the numerator first. So the numerator is this, and it's a polynomial, right? This is a polynomial. Now, because it's a polynomial, it means that what it's we have no problem with this function, right? It exists everywhere. Everywhere. So any XY combination would work for this function. What I mean by that is, let's say I can pick any coordinate for X and Y, and I'll be able to evaluate this X squared plus Y squared plus 1. So I can pick for example, -1, 1, 0, 2, choose any number that you want, right? -3. You could check all of this and you find out that this function exists for all these numbers, right? Because polynomials so what I'm saying is, check all of this can be evaluated. All of this can be evaluated. You see what I'm saying? +1. You can also evaluate this, which is -5 square plus -3 square plus 1, right? All of these things will exist, right? So we have no problem with the numerator. Okay, now the denominator is where we are going to, try to constrict the domain where we remove some points that where the function might not exist, right? So we need to look at the denominator now. So denominator actually says we have this function 4 minus x squared minus y squared minus z squared. Is it minus z squared? Yes. So this is a function of f x, y, z. So let me just add that. Okay. Now, when you look at this, now we already said that we already said that when we have a fraction, right, it will not exist when the denominator is 0. So the first thing that we need to note is what? For the domain, the first thing we need to note is all points where when this so this must not be equal to 0, right? The points that make this to be equal to 0 will not be part of this domain. That's the first thing that we need to note. This should not be equal to 0. Now, so that's the first part, not when. So the first part is what? This must not be equal to 0. Now, the second thing is we have a square root, which is an additional information, which means that what? For the square root to exist, for the square root function to exist, the inside of the square root, the inside of the square root must be greater than or equal to 0. These are the two things, right? Now, when you combine these two, it means that what? We know that what? This square root of this function must not be equal to 0. Now, the square root will be equal to 0 whenever we have the equality, right? Whenever 4 minus, so when 4 minus this equal to 0, the equality part, when this is equal to 0, this is when this will also be equal to 0. So to combine these two conditions together, we have the third condition, which means the domain exists for the points where this must be greater than 0. Okay, so domain exists if this is true, and this is what we concentrate on. Okay, because let me just reiterate this one more time. First of all, we know that because we have division, so we have division, we have fraction, it tells us that what? The denominator must not be equal to 0, right? Because when it is equal to 0, those points that make them equal to 0 will not be part of the domain. So we already ascertained that what? This must not be equal to 0. And then on top of that, we also have a square root there, which tells us that what? For us to be able to evaluate this square root, the inside of the square root must be greater than or equal to 0. Okay, so the domain will exist whenever the inside of this will be greater than 0. If it is equal to 0, the domain will not, those points will not be part of the domain, right? So you can check, you can try to evaluate those points, right? And I will explain at the end of this what are those points that what are those points that would make this square root function to be equal to 0. Okay, which is basically the points that satisfy this equation. Okay, now we already know that what this was what the domain will contain, right? Only the points that satisfy this inequality would be in the domain. So therefore, we can simplify this, take the rest to the other side, and which will mean that what? So when we write it in this form, this means less than 4, and we can write it one more time to make it very clear what is happening. This. Now, what does this mean? Now, this is equation of what? This means we have, this means inside a sphere, right? Inside of a sphere, right? Because for a sphere, we have x squared. So for example, let's say we had equality, that would be, so the equality part will give us the equation of a sphere with radius 2 centimeters. But this would be the inside of that sphere without the boundary. You can see that what we are having a sphere where the boundary is not included in this as part of this domain. That is basically what the function, what the domain of this function is. So we can quickly just finalize it. So the domain of this function contains all x, y, z such that x squared plus y squared plus z squared is less than 2 squared. And to describe this, this is inside of a sphere of radius 2, basically. So that is the solution to that first problem. Okay. Now let's check the second one. Second one is a little bit easier than the first one. It's of a different flavor. So let's so you can see the function here. So let's look at it. Now the problem we have with the second one is just the denominator. The numerator is fine. You can check the numerator. It's just a polynomial. So this exists everywhere. It exists everywhere. Now, what we need to be wary of is the denominator. We know that our denominator must not be 0. So all points that would make denominator equal to 0 will not be part of this domain, right? So this must not be equal to 0. That is when the points that will satisfy this would be part of the domain, would be the domain itself, because you remember that what this one exists everywhere, so it means we have no restriction on x squared plus y squared. But for this, the restriction is this: for the points in the domain must include what? All xy, such that what? X squared minus y squared multiplied by this is not equal to 0. This is basically what the domain is. But we can do a much better work to try to illustrate in terms of lines and curves that will satisfy this particular condition. Now let's express this. So it means this, either this is not equal to 0, these two, or this is not equal to 0. Okay, that's what it means, right? What usually happens is you solve the reverse of this, which is the part where the function will be undefined, which is when equal to 0, or x plus y minus 1 equal to 0. Whichever one you solve is fine. You just need to make sure that you put the right one here. So in the domain, so for the domain, for the points to belong to the domain, it basically means all points x, y that would make sure that x squared minus y squared is not equal to 0, as well as x plus y minus 1 not being equal to 0. Okay. Now, what do we get from the first one? This means x squared equal to what? Y squared, which means that what? Must not be equal to y squared, which means that what? Y must not be equal to plus or minus x. So when you take the square root of both sides, this is what you have. Okay, so that's the first function, y equal to x, y equal to minus x. So those things must not be equal. So y must not be equal to x and must not also be equal to minus x. Okay. Now the second part is when you solve for y, it will give you minus x plus 1. So y must not be equal to this. So I'll just take x to this side, take 1 to this side, I will have this. So this is the second condition. Okay, so we can back up now and write our domain. So our domain basically contains all xy, any point except the ones that satisfy y equal to or minus y equal to plus or minus x, and y equal to minus x plus 1. So that will be the domain of the second function. All right. I hope you understand the video. If you have any question further than this, you can comment down below for me to to explain certain parts that are not well understood by you. And then don't forget to like and subscribe to the channel to allow its growth, and also share in other platforms to allow other people to be able to see this channel. So thank you very much for today's video. I will see you guys in the next one.